In this video, we will do the viscous scaling of the Navier-Stokes equations. Recall that in the previous video, we derived a form of the normalized Navier-Stokes equations using an inertial scale where we divided everything by the term that multiplied the material derivative, and then we said that delta P scales as rho v0 squared, and that gave us the inertial scale. And from that we obtained the dimensionless form of the momentum equations. And I'm going to drop the star term just for simplicity. U dot grad U equal minus grad P plus 1 over the Reynolds number del squared U plus 1 over the Froude number squared G. Okay, so in this case, so G over here is just essentially a direction vector for the gravitational component. And in this case, we said if the Reynolds number is very high, then this term is negligible, and then we obtain the Euler equations, what people call inviscid flows. That's technically incorrect. It's flows where viscous forces are negligible compared to inertia. Now, one might argue we can also use this equation for the case when the Reynolds number is small. And if that's the case, then you would get Reynolds number times du by dt, material derivative, equal minus Reynolds number grad P plus del squared U plus Reynolds over Froude squared G. And in the event that in the case that the Reynolds number is really small, this implies that, so if Re goes to 0, this implies that del squared U is equal to 0. Okay. Now this is this doesn't give us any interesting results because it's really an incorrect way of interpreting this equation, and this is incorrect because we missed on one very important thing over here, and that's the scaling of the pressure. Remember, this pressure was scaled. This pressure had a delta P over rho v0 squared, and we said that that's equal to 1. When you multiply by the Reynolds number and then subsequently say that the Reynolds number is vanishingly small, you are taking out this term, yet we have assumed that this term is scaled by inertia, which is negligible in this case. Rather, what we should have done is scale this term using viscous forces, and then we would see, and we will show that this term does not disappear in that case. Okay, so let's go ahead and do that. Recall that the dimensionless form of the equations, what we ended up with was rho v0 squared over L0 into du star by dt star. One tip to get rid of all these stars is to write the dimensional equations as starred variables, and then define the dimensionless terms without stars, so that essentially you get rid of all the starred terms. But let's keep the stars now for this discussion. Equal minus delta P over L0. Remember, this is unknown at this point. Previously, we had said that we're going to divide everything by this term because inertia is dominant. But we're not going to assume that over here. Rather, we're going to take this guy over here, the viscous scale, plus rho G, G vector. So previously we asked the question, okay, what do we divide this equation with so that we can balance terms? We said that if inertia is dominant, then we're going to divide by this term. In this case, viscous forces are dominant. So we want to divide by mu v0 over L0 squared. And what that means is multiplying by L0 squared over mu V0. So we get L0 squared over mu V0 times rho V0 squared over L0 du by dt is equal to minus L0 squared over mu V0 times delta P over L0 plus there's a grad P over here, plus del squared U plus L0 squared over mu V0 rho G times G star. Okay, so now we can start simplifying terms. This guy cancels out with that guy. This velocity cancels with this guy. And this gives us rho L0 V0 over mu, and that's the Reynolds number as expected by dt star equals to, now this term, yes, of course we can cancel the L0s, but we're going to also again say that this term is going to balance with the viscous terms because we want a driving force, and therefore we're going to assume that this whole thing is of order 1. So of order 1. So this implies that delta P L0 over mu V0 is equal to 1. So this gives us the scale for delta P, and that's mu V0 over L0. That's a viscous scale. And therefore, this term becomes grad P, and then we would have the diffusion term plus, now this guy is interesting. I see viscosity, velocity, length scale, so that indicates the presence of a Reynolds number, but I also see gravity, which indicates the presence of a Froude number. So here's what we're going to do. We're going to do L0 squared over mu V0 rho G. What we're missing is, so we have a rho, we have an L0 up here. We would need a V0 to get a Reynolds number. So we're going to multiply by V0 and divide by V0. Now rho V0 L0 over mu gives us a Reynolds number. And then what we're left with is a G L0 over V0 squared, which is 1 over the Froude number squared. So that gives us Reynolds over Froude squared. Okay? Over Froude squared V star. Now this is a much better looking equation because as the Reynolds number approaches 0, okay, we can still have a driving force given by this grad P. So as RE approaches 0, then we get a balance between viscous forces, del squared U equal grad P, and div U equal to 0. And those are the Stokes equations for creeping flow. The reason we say creeping flow is because the material derivative, the advective terms, essentially disappear from this equation. This is a very important set of equations because although they are four-coupled PDEs, they are linear, which means we can use the principle of superposition to solve problems. So for example, if you have flow over a rotating cylinder, so you have creeping flow over a rotating cylinder, okay? So that is equal to, this is V infinity, that's equal to the flow over, and this is omega 0, flow over a fixed cylinder plus the quiescent flow driven by a rotating cylinder, V infinity equals 0. Okay, so that's the principle of superposition. And just to give you an idea when this Stokes flow is important, let's look at a swimming human. Remember, you're just thinking about the Reynolds number, not the viscosity on its own, not the velocity. It's the relative importance of inertia driven by velocity advection compared to the resistance of the flow compared to viscosity. Swimming human, Reynolds number is about 10 to the 4. Goldfish, swimming goldfish, is a Reynolds number is about 10 to the 2. Swimming microorganism, like a bacteria, microorganism, Reynolds number is about 10 to the minus 4, and that's very small. So indeed, microorganisms live in the Stokes flow regime. There's a paper called Life at Low Reynolds Number that I will send out to you shortly that talks about life for microorganisms. And there's a very important result out of Stokes flow that impacts all sorts of microorganisms. And that has to do with the fact that Stokes flow is reversible. So let's say you have a microorganism that propels itself by, closing and opening its flaps, for example. So, you'd have something like this. And so let's say the organism, if it opens in the outer direction, then it thinks it's going to propel in that direction, and it does. And then it closes. Then when it closes, it's going to propel it back in this direction by exactly the same amount. So the bacteria, the microorganism, doesn't have any motion. And that's why you see bacteria, they have these little flagella, which are like a directed corkscrews that will essentially break the symmetry of the flow and allow the microorganism to move around. Other important Stokes flows are flows in porous media, flows within cells, flows around polymers, nanorods, etc. But this reversibility doesn't actually hold for non-Newtonian fluids, so just as an FYI.